Hello, welcome back again to the channel. In this video we're going to discuss about the Supremum. Okay, so by definition, first we need to define what is an upper bound and what is a lower bound. So if we have a subset of real numbers which is non-empty, and so we call an element in, so make a mistake, should be an element in R, is called an upper bound of S if this element is greater or equal every other element of S. And similarly, a lower bound of S, so Y is a lower bound of S if Y is smaller or equal to every element in S. So this makes sense, the definition makes sense. And then we call the lowest upper bound, we call it a supremum, and the lowest upper bound, and there is greatest lower bound. It's called infimum. Okay. So the lowest upper bound is defined as the smallest upper bound. What does the smallest means? It means that if we have another upper bound for S, then this upper bound has to be greater or equal to this lowest upper bound. Okay, and we can have a different definition. We can right away use this as definition, or we can prove it that this definition and the definition that I'm going to give is an equivalent definition. So Z is equal to the supremum of S. Let's use this kind of notation. If first Z is an upper bound, and second, so imagine that we have a bunch of points here. This should be our S, and we have our Z here. Okay, so this guy will be our lowest upper bound, which is the supremum of S, if for every other element to the left of this Z, let's say we have the number t here, okay, since this t is smaller than Z, then this t cannot be an upper bound, right? Because by definition, another upper bound of S has to be greater or equal to Z. Okay, so this t is not an upper bound. So let's call it for all t less than Z, t is not an upper bound. What does it constitute when we say that t is not an upper bound? It means we can find an element of S which is bigger than t. Okay? So in order t is not an upper bound, there have to be an element of S that is bigger than t. That is S0 S such that t less than S0. Okay? So in order to verify that a certain number is an upper bound, we need to check that that number is indeed an upper bound. And secondly, for every number less than the one that we suspect to be the upper bound, that number has to be not an upper bound. Okay? So let us look at several examples. If S is equal to just a finite subsets of R, let's say minus 1, 0, 1, 5, 6, for example, we can easily see that the supremum of S is 6. Meanwhile, the smallest lower bound of S is minus 1. Right? And we can verify using either this definition or that definition, that they are indeed correct. Okay. Another one, if another set, let's say, is the interval, this capital T is the interval from 0 to 1, including 1 but excluding 0. So, what is the infimum? The infimum of T is 0. Okay? Because if, imagine, this is not really a rigorous proof, but we need to use our common sense in order to come up with a rigorous definition. So, we claim that the infimum of T is equal to 0. Okay? And we can see why. First of all, this 0 is indeed a lower bound of this set, right? Because every element in here is greater or equal to that 0, right? And secondly, if we move to the right side, so this one is an equivalent definition for infimum. So let me recap probably. So remember that is the definition of the supremum, and the infimum is the greatest lower bound. Meaning, in order to be a lower bound, in order to be the greatest lower bound, first of all, the guy needs to be a lower bound, and for any other lower bound, the other lower bound should be smaller than this guy, this infimum guy. Or, using this definition, if you want to use infimum, let's say the infimum is here. If we move to a certain point to the right of the infimum, let's call it V here, then this V is no longer a lower bound. Right? So, okay. So our claim is that 0 is our greatest lower bound, or our infimum. Why? Because it is a lower bound. And secondly, if we take any number to the right side of 0, let's call it V, similar to that one, then suddenly we can find here an element of T, right? So that's the reason why we know the infimum of T is 0 and the supremum of T is equal to 1. This can also be verified rigorously. What I'm trying to say here is that the supremum and the infimum, sometimes the number is belong to the set itself, but in another time it can be happen that the infimum or the supremum is not belong to the set. So notice that the infimum of T is equal to 0, which is not an element of T, correct? Okay, so basically if we have a weird set which is not easily determined what is the infimum or what is the supremum, then the method to find the infimum is by guessing. I mean, you need to study the set itself and come up with a reasonable guess what is the infimum and what is the supremum. And then we claim that our guess is correct by showing either the definition of the supremum is satisfied or the definition of the infimum is satisfied. Okay? So now in real number we have the following axiom of supremum, which says that, so we have an axiom that every subset of R, as long as it is not empty and bounded above, has a supremum. But we can prove that the supremum is unique, so we can say it that has the supremum. Okay. And similarly, we can also right away, even though we only have one half of the axiom, which is only talking about the supremum, but we can verify that this is also implies that whenever we have a subset of R which is non-empty and bounded below, then the set must have the infimum. Okay. Okay. So now, naturally, we would like to know what is the property of the supremum and infimum related to the operation in the reals. Okay. So, for example, we can define given a set S, say, and A in R, for example, define A plus S to be the set of all numbers of the form A plus S, where small s belong to the capital S. And A times S will be A times S, where S belong to the capital S. So the question is that what is the relationship between the supremum of the following two sets and the supremum of S? So what are the relations between, say, sup of A plus S and sup S? Okay. In order to realistically come up with a certain relation, we need to study some toy model of S and with a certain A. So just play around with several examples, and then after we play around with those examples, then we can probably come up with a certain statement that relate these two numbers. Okay? So let's say that our S is, let's say, what? Interval from 0 to 1. Okay? And then if we take A equals to 2, then this interval, by adding 2 to each of these points, will become new interval 2, 3. So this is A plus S, right? And this is S. So here the sup of S is 1, and the sup of 2 plus S is 3. Okay. So since this is 1 and that there is 2 here and there is 3, so it is reasonable to guess that the sup of 2 plus S is the same as 2 plus sup S. Okay. So that's our guess, the relation between the supremum of A plus S and the supremum of S. And probably one example is not enough. Probably we need to play around with more examples to give us more confidence whether this statement is correct or not. Okay, but let's assume that we played enough and then we feel that it is a correct statement. So, and we want to propose this proposition that the supremum of A plus S is equal to A plus supremum of S. Okay. Okay, so let's think about how to prove this kind of relation. Okay, so one way is that we look at to this number, and if we want or if we claim that this number is indeed the supremum of A plus S, then we need to show that this guy is exactly satisfying the definition of supremum of the set. Right? Meaning we need to see if this number if this number satisfies whether the first definition of the second definition of the supremum. Okay, so that's one way to prove this relationship. And the other way is by showing that this number is less equal to that number, and this guy is less or equal to this guy. Okay, so that's the two ways that we can think of to prove this kind of relationship. Okay, so let us try to use the first method, which is basically asking, is A plus sub S the supremum of A plus S? So let's recap again what it is. What does it mean to be a supremum of a set? So that number first needs to be an upper bound. So let's check. So then answering this question is the same thing as answering the first question. Is A plus sub S an upper bound of S? Okay, let's find out. Okay, so we want to show that A plus supremum of S is an upper bound of A plus S. I'm sorry. So how do we show that a certain number is an upper bound? We need to show that this number is greater or equal to every element in A plus S. So we need to take any, let's say, x in A plus S. So because x is in here, we can write x as A plus t for some t in S. We don't know what is the t, but there is a t, so that x equal to A plus t for some t. Okay? If we can show that this x is smaller than A plus sub S, then we are there. Right? Now, notice, since sub S is an upper bound for S, then clearly t is less or equal to the sub S. Why? Because t is a member of S. Meanwhile, the sub S is an upper bound of S. So every member of S must have to be less or equal to this guy. Okay? So therefore, A plus t is less equal to A plus sub S. Okay? And this works for every t in S. Hence, A plus sub S is an upper bound of A plus S. Right? So, we already verified that this A plus sub S is indeed an upper bound of A plus S. And secondly, what we need to show that is, if we take any element less than A plus sub S, that element cannot be an upper bound of A plus S. So, okay? So let's prove it here. So suppose what? We need to take any number smaller than this. Suppose what letter that we have not used yet. Let's see that. Suppose B is less than A plus sub S. Our objective is to show that B is not an upper bound of A plus S. Okay? That's the meaning of a number to be a supremum, that it is an upper bound, and for any other number that is less, that's simply less than this guy, that number has to be not an upper bound. Okay. Okay. So this is our starting point, and this is our ending. We want to show that B is not an upper bound. If we can show that, then we have verified that indeed A plus sub S satisfying the definition of the supremum of A plus S. Okay. Okay, suppose B is less than A plus S, then B minus A less than sub S. Okay, by definition of supremum, there is. Okay, so remember that if we take any number smaller than a supremum, then this number is no longer an upper bound. What does it mean it is no longer an upper bound? It means that we can find an element of S that is greater than this number. There is S0 in S such that B minus A is less than S0. Hence, B is less than A plus S0. And this A plus S0 is an element of A plus S. So what does it mean? It means we can find an element of A plus S which is greater than this B. And therefore, B is not an upper bound of A plus S. So we are done. So we just show that this guy, A plus sub S, is indeed satisfying the definition of the supremum of that set. Okay, so that is the first method to prove an equality between supremum. And the second method is by showing this guy is less or equal to that guy, and this guy is also less or equal to that guy. So let's do it. We want to show that we don't know. Let's just do it naturally. So how to do that? So take S in S, then A plus S. Okay, then S is certainly smaller than the supremum of S, correct? Because the supremum is an upper bound of the capital S. Hence, A plus little s is smaller than A plus sub S. And this is true for all A plus S in A plus capital S. So what does this inequality says? It says that A plus sub S is an upper bound. So A plus sub S is an upper bound of A plus S. Okay. So remember that the supremum is the smallest upper bound. So therefore, because supremum of A plus S is the smallest upper bound, then compared to another upper bound of A plus S, this guy is still smaller or equal. Hence, why we can imply this? By definition of supremum. Okay, so we just show that this is less equal to that. Okay, now we need to prove the other way around. And how we do that? Let me think. So we want to show that A plus sub S is, so we claim that a plus sub s less or equal to sub a plus s. Okay, and this statement is equivalent to sub s is less or equal to minus a plus sub a plus capital S. Okay. And we can show this if we are able to show that minus a plus this. So it is enough to show that minus a plus sub a plus s is an upper bound of s. Okay? Why is that so? Because if this is also an upper bound of s, then every other upper bound of s will be bigger or equal to this sub s, meaning that we have this inequality. Okay, so then we just need to show that every element in S is smaller than this guy, right? So let S in S, okay, then A plus S is smaller than sub A plus S, which is true, right? Because this guy is an upper bound, the smallest upper bound of all elements of this form. Okay, but this is equivalent to S less or equal to minus A plus sub A plus S, meaning that this guy is an upper bound. Is an upper bound of S. So we are done, right? Why? Because since this guy is an upper bound of capital S, then compared to the smallest upper bound of S, this upper bound still bigger or equal to that smallest upper bound. So we have two inequality. Oh, hold on. Where are the inequalities? So this one and this one. So we are done. Okay. So that's the two ways of how we can prove the relationship between supremum or between infimums. Okay? And you might check whether the other statement is still correct. So if we replace this addition with multiplication, and we can ask whether the statement is still correct or not. Okay? So you may probably want to try it first. And you can write a comment if you are able to prove or disprove this statement. Okay, thank you so much for watching. That's all for now. If there are many people who like this video, we can make several videos even about real analysis. Okay, thank you for watching. Don't forget to subscribe. See you again in the next video. Bye bye.